In this video, we'll look at a couple more calculations with calorimetry, or heat transfers. Here is a neutralization. We have 50 milliliters of 1 molar hydrochloric at 25 degrees Celsius added to 50 milliliters of 1 molar sodium hydroxide at 25 degrees and a coffee cup calorimeter. We're using a styrofoam cup because it's a better insulator than glass. We'll do that in the lab too. After the reactants are mixed, the temperature increases to 31.9 degrees Celsius. Assuming no heat is lost by the calorimeter and the density of the solution is 1 gram per milliliter, how much energy was released by this reaction? I can't wait to calculate. Again, they're assuming no heat loss because that is always a major source of error when you're doing some kind of an energy transfer type of lab or experiment. So that's, again, why we use styrofoam. There's a lid on the cup. We try to keep this as insulated as possible. Then also at the end, we want to calculate the enthalpy change per mole of HCl. Okay, so it's a transfer of energy from the system to the surroundings. The system are the reactants and products, all the components of the chemical reaction. In this case, the hydrochloric acid, the sodium hydroxide. The surroundings, in this case, are mostly the water in the solution. So we could easily calculate the amount of energy, we could say heat energy, absorbed by the surrounding water, the water in the solution, this temperature change. Like when we put the thermometer in the solution, we're measuring the temperature of the water primarily. So the temperature went up. Again, that's the temperature of the water going up. So let's do this. Let's calculate Q equals mass times specific heat times delta T. Q equals mass of the total solution. They tell me that I can assume the density is 1 gram per milliliter, which you can always assume if they don't tell you. We combined 50 milliliters of hydrochloric with 50 milliliters of sodium hydroxide. Is it okay then that we have 100 milliliters of total volume? And if the density is 1 gram per milliliter, is it okay if I say 100 grams? And then we'll multiply by specific heat. And again, in most solution problems like this, they might specify that you can use the specific heat of water because most of the particles present are water. In this case, if they don't specify that, it is a fair assumption. We're going to use 4.18 joules per gram degrees Celsius. It's the specific heat of water. But again, with these solution problems, you can use the specific heat of water. And then our temperature change will be final minus initial. 31.9 minus initial, both are at 25. So let's say a 6.9 degree temperature change. So that was the 31.5 minus 25. Final minus initial. So we plug all this in, and we get 2,900 joules of energy. And again, with these thermo problems, you get your final answer, which is great, but we also need to indicate the direction of the energy flow. This was energy absorbed by the water, which must have meant that the reaction itself was exothermic, which they kind of hint. How much energy was released by the reaction? So here's the amount that was absorbed by the water. It's also the amount released by the reaction. So you could either do this. You could write 2,900 joules released. Or you could say Q equals, for the reaction, negative 2,900 joules. Okay, for the reaction. So somehow we have to specify the direction of the energy flow. It was transferred from the reaction, from the system, to the surrounding water. So for water, the temperature change was positive. Water absorbed energy as it was released from the reaction. Now the last part of this, they want me to calculate the enthalpy change per mole of HCl. Oh, this is minor. So if I take that original solution, it was 1 molar hydrochloric, which is moles per, let's see, what do we have, 50 milliliters? So 0.05 liters? We could cross multiply and solve this thing for moles. So we had, that's easy, 0.05 moles of HCl. So now if they say per mole of hydrochloric acid, we could say, and actually I should double check. How much energy is released? Calculate the energy change per mole. Now sometimes you have to be careful. They might say in units of kilojoules per mole, or in this case they don't specify. So I think we're okay if we just leave it in joules. So we could say that this would be negative 2,900 joules divided by 0.05, 500 moles. And then that would come out to be negative 58. If we just leave maybe 2 sig figs, we could say 1,000 joules per mole. Or again, it's kind of common. Sometimes at the end they might specify, hey, we want this in units of kilojoules per mole. And then we'd say, okay, how about negative 58 kilojoules per mole? It's one of those things that people miss, and then they get the test back and they lost a half a point. They slap themselves in the face. They're like, I was a bonehead. I missed that. This one didn't specify. Just says calculate the enthalpy change per mole of HCl. So either of those would be acceptable if they didn't specify a unit. There, piece of cake, right? All right, let's try one more. This one's kind of fun. Here's a precipitate problem. Holy moly, we got a lot going on. A liter of 1 molar barium nitrate solution at 25 degrees is mixed with 1.5 liters of 2 molar sodium sulfate solution, also at 25 degrees, in some kind of a calorimeter. The white solid barium sulfate forms. There's my precipitate. The temperature of the final mixture increases to 28.1 degrees Celsius. We don't often check the temperature change in a double replacement, or are we forming a precipitate? But one of the requirements of a chemical reaction is that there is an energy change. Often, in this case, it is something exothermic. Assuming no heat is gained or lost by the colorimeter or the surroundings, and the density of the final solution is 1 gram per milliliter again, calculate the enthalpy change per mole of barium sulfate formed. And now here they kind of tell me that I can assume the specific heat of the solution is the same as water, 4.18 joules per gram degree Celsius. The majority of the particles are water molecules. Okay, so again, it's very similar as the last one. The temperature of the surrounding water increased, so the reaction itself is exothermic. It's easy to calculate the heat energy absorbed by the solution, which will be primarily water. So let's go Q equals mass. Okay, so it's 1 gram per milliliter for the solutions. We started with 1 liter of barium nitrate and 1.5 liters of the sodium sulfate. So we have 2.5 liters total volume. Now in the end, when we use the specific heat, it's in units of joules per gram degree Celsius. The density is 1 gram per milliliter. So is it okay then that we say this is 2,500 milliliters? And then the mass would be 2,500 grams. Another common mistake that people just overlook, they'll plug that in as 2.5. They're thinking along the right lines. The density is 1. It's 1 gram per milliliter. So we want to change that from liters to milliliters, and then we got the mass. Specific heat, we can use 4.18 joules per gram degree Celsius. And then the temperature change. We're ending at 28.1 and we started at 25. So how about a 3.1 degree temperature change? Final minus initial. So if we plug this in our calculator, and I don't know, maybe 2 or 3 sig figs, we could say this is maybe like 32,400 joules absorbed by the solution. Well, that also is the amount of energy released by the reaction. For the reaction, it's exothermic. We'd say it's negative 32,400 joules. And again, they don't specify, so I wouldn't mind. You could also say negative 32.4 kilojoules. And now that's released by the reaction. So you could either write the negative 32,400 joules, that's the energy change for the reaction, it's exothermic, or you could say released. You could say there's 32.4 kilojoules released by the reaction. As long as you do one or the other, indicate the sign of the delta H, because if you leave that negative out, we'll assume that it's positive. It's positive for the solution of the surrounding water, but for the reaction, for the production of this barium sulfate, that's an exothermic process. Okay, so any of these would be fine. Here's the energy change for the reaction. The only other part of this that we might want to check, and again, here's something that people will overlook. They'll be like, gosh, this was easy and I'm moving on. Per mole of barium sulfate formed. Oh, well, we didn't really check that. Enthalpy change per mole of barium sulfate. Here's the total energy change for the reaction. How much barium sulfate is formed? Was there 1 mole? Well, then we're done. But what if there were like 2 moles of barium sulfate formed? Well, then I'd have to divide that by 2 so that I got per 1 mole of barium sulfate. So here's the fun part of this one. We got to do a little check here and figure out, with those quantities listed, how much barium sulfate would be formed. Ooh, I can't wait. So let's double check the balanced equation. In the balanced equation, I would have barium sulfate formed from a reaction of barium nitrate, NO3, and sodium sulfate. Excellent. Double replacement. We would get, how about 2 of these sodium nitrate and the barium sulfate. Fabulous. Just what I expected. So again, now we need to kind of go look back at what we have and see what's limiting, what's excess, how much barium sulfate should we be able to form in this situation. All right, so let's go back up and look at our original problem here. I have 1 molar barium nitrate. This is kind of the fun part. A little solution stoichiometry. That's moles per 1 liter, which gives me then, oh, perfect, 1 mole of the barium nitrate. And then I do the same thing with the other one. It was 2 molar sodium sulfate. That's moles per 1.5 liters. So if I cross multiply, that gives me a big fat 3. 3 moles of, excellent, sodium sulfate. Okay, so we better look at the ratio from the balanced equation and figure out with these amounts how much barium sulfate would I form. Okay, so the two reactants in the equation are a 1-to-1 ratio. I do not have a 1-to-1 ratio. I have excess sodium sulfate. So sodium sulfate is my ER, my excess reactant. And then barium nitrate would be my limiting reactant. Oh, that's a blast from the past, huh? That's like a little chapter 4, solution stoichiometry. Figure out moles in your solution. Look at the ratio in the balanced equation. Do we have a limiting? Do we have an excess? We do. So we would use the limiting reactant then to figure out the amount of product formed. Which, what do you know? It's our lucky day. In this case, we actually have 1 mole of barium nitrate, and it's a 1-to-1 ratio between barium nitrate and barium sulfate. So what we just calculated really was per 1 mole. Either of these were for 1 mole of barium sulfate. I'll put that in there, for barium sulfate. Now, again, we got lucky. It wouldn't have to be 1 mole. Let's say this was a different ratio in the balanced equation, and what we just calculated would have been for like 2 moles of barium sulfate. Well, then if they wanted the energy change per 1 mole, we would have to divide by 2. Or if we only formed half a mole, then if they wanted the kilojoules per 1 mole, we would have to multiply by 2. So just something to watch out for. Double check the ratios, double check the balanced equation, and see, okay, with these amounts, how much barium sulfate would I form? Because that energy change then is per moles that you would form using those amounts given. In this case, we were lucky. The limiting reactant was the barium nitrate. We had 1 mole, so we would only produce 1 mole of barium sulfate.